I'm Jen Blank, and on behalf of Adrian Brown, Cynthia Phillips, and Frank Marchese, we organized this symposium. I'd like to welcome you today. Today our speaker is Julie Chittenden, and she's a postdoctoral research fellow at NASA Ames Research Center. Julie did her undergraduate degree at Arkansas State, and then went on to do her PhD in planetary sciences and chemistry at the University of Arkansas in the Center for Space and Planetary Sciences. She's been here since 2007, I believe?
2008.
2008,
Mm-hmm.
and is working on a variety of projects, one of which she's going to talk to you about today. Just before we start, I just want to remind people that this is a recorded seminar, so you'll be able to look at it or find it on the SETI.com, or SETI.org rather, website in about a week's time, and listen to the whole thing again. And also, because it's recorded, we ask that you save your questions till the end of the talk, because those will be recorded as well. And we found that if you interrupt the seminar with questions, it results in sort of boring pauses in the audio recording. And also, this microphone is not, it's actually a recording device rather than a speaker. So I'll be passing this microphone around at the end of the talk. So without further ado, here we go, Julie. And the title of her talk is Investigation of the Effect of Dissolved Salts, Regolith Layers, and Wind on the Evaporation Rate of Water on Mars.
Thanks. Okay, hello. How are y'all? I have to do my southern greeting. Hi, y'all. This was the research that I did for my dissertation work at the University of Arkansas. I've gone on to start a few other projects here at Ames. So I'm going to talk about a few things. I want to give you guys a short introduction just about why we did this research. I'm going to go on to talk about the evaporation rates of low concentrations of brines, and how we compared that to the evaporation rates of pure water that we measured. And we went on to to do experiments on eutectic sodium chloride and calcium chloride brines. And we moved on to looking at sublimation of water ice through JSC Mars 1 regolith. And the last experiment we did was the effect of wind velocity on sublimation rate of ice. And I'm going to briefly go over some possible future work. So the purpose of these experiments, at the time that we started these experiments, there wasn't a lot that was known about how water behaved under Martian conditions. There were a lot of speculation of whether or not if you had a liquid water reach the surface, whether it would instantaneously boil and evaporate off, if it would freeze, what would happen. So what we wanted to do was put the water under Martian conditions, see what happened, and characterize it. And we know there's water on Mars. This is a water map. This was taken in 2006. And keep in mind that this goes from plus 60 to minus 60. So we know that there's water on Mars. We just didn't know how it behaved. We used our planetary simulation chamber to do all of our research at the University of Arkansas. This is a 7-foot by 2-foot chamber. So it's really large. It's much easier to control. It gives a lot of headspace, and we were able to control the humidity inside the chamber very well with that. It had 9 thermocouples. There were 5 thermocouples that were along the side of the chamber. We had 2 thermocouples inside the atmosphere, measuring the temperature of the atmosphere inside the chamber. We'd always have one thermocouple in the sample. And at the time, we were using a methanol dry slurry as our coolant. It's since been upgraded to a cooling system, but we would use this methanol dry ice slurry and pump it around cooling coils that were wrapped around the chamber, which was surrounded by insulation. We also had a hygrometer inside the chamber to measure percent humidity. It's really important when dealing with water samples under Martian conditions. We don't want to saturate the atmosphere with water and therefore not have a Mars atmosphere. We had a Brine pressure gauge to measure the atmospheric pressure inside the chamber. We had two cameras, so we can take a look at what our sample was doing. If we had a sample of water, is it explosively boiling? Is it freezing over? What is it doing? We used an analytical balance to measure mass loss rate over time. And we had a CO2 atmosphere. Basically, you pump it down to vacuum, fill it with CO2, cool it down, and we would open the chamber up, put our samples in, whatever kind of sample we would be using at that experiment, close it up, pump it down to 7 millibars. Most of our experiments were done at 0 degrees Celsius. For the temperature dependence, we went down as low as minus 25. Okay, so at the start of our simulation experiments, little was known about the types of salts on the surface of Mars. We had some idea, but we wanted to look at Earth first. Like, what do we see here on Earth, and can that be correlated to what's on Mars? So the first thing we did was we took a look at all the saline bodies on Earth. The oceans, for reference, are about 0.5 molar, which correlates to 19.35 grams of chloride ion per kilogram of water. We do have some places on Earth that are lower in saline concentrations, like the Baltic Sea and the Black Sea, but there are also places on Earth where we have a very high concentration of salt in our waters, including the Great Salt Lake is slightly elevated, but especially the Salton Sea, the Dead Sea, and especially Don Juan Pond down here in Antarctica. Don Juan Pond is a eutectic calcium chloride pond that never freezes. So that is really exciting, because if we can have a calcium chloride pond on Mars, maybe early Mars, possibly present day Mars, who knows, it could stay liquid on the surface at those temperatures. Then we took a look at what we knew about salts on Mars. At the time, the spacecraft data had shown high levels of sulfur and chlorine. When you looked at Martian meteorites, especially Nakhla, they saw traces of halide sulfate and carbonate salts. In addition to that, there were experiments that were run by Bullock and Moore, and what they did was they took a crushed Mars regolith simulant, and I'm going to simplify it, but pretty much soaked it in water to see what anions and cations leached out into the water. I mean, it's a lot more complicated than that, but what they found, and through all the reading we did, the main cations that we wanted to look at were sodium, calcium, and magnesium. And the major anions that were found were chlorine, sulfate, and carbonate. And this was before, of course, Phoenix mission landed, so we weren't looking at perchlorates at the time. So we decided to start with the chloride brines, especially sodium chloride and calcium chloride. They were easy to get a hold of, they were easy to work with, and they stayed liquid at very cold temperatures. So the first thing we wanted to do was test the effect of a low concentration of brine. On Earth, like I said, the oceans are about 0.5 molar. So we wanted to kind of look at what if there had been an ocean on Mars. It would have been a low concentration. Let's start there and see what happens. So we started with a 0.25 molar sodium chloride brine, and then we wanted to take that and compare it to previous experiments that were done on pure water. Okay, this was our setup. This was our original setup before we had to move the chamber. It's pretty much the same setup. What we did with the sample, we had a beaker and made sodium chloride ice cubes. Okay, you crush them up, you put in a beaker, you add the 0.25 molar sodium chloride solution, and we had a wire mesh to keep the ice from the surface. The reason why we did that, we wanted to make sure that our sample temperature was at the atmospheric temperature. So we didn't have a really warm sample in a really cold environment, or vice versa. So that was our way of controlling the sample temperature. We had two different versions of this experiment. We had what we called with advection and without advection. Now, what I mean by that is we had wanted to look at what the possible effect of wind would be. So we were trying to forcibly remove the water vapor from the surface of the sample. To do that, we put a bag of dry ice inside the chamber. Well, it turned out that it was a very good sink for the water vapor in the chamber. It ended up acting kind of like a cold finger. So when I say with advection, it's more of a low humidity environment, and without advection, it's more of a high humidity environment. And what we saw was that these are the experiments that we ran. The solid line is the evaporation rate of pure water, and the shaded area is with the uncertainty. So you can see that within the error bars, they're pretty similar. We didn't see a whole lot of change. So since we didn't see a whole lot of change, we wanted to move on and take a look at more concentrated brine solutions. The great thing about eutectic solutions is that they can stay liquid at very cold temperatures. Sodium chloride freezes at about minus 21 degrees Celsius. Calcium chloride freezes at almost 50 degrees Celsius. So we can put it under very low temperatures and see what kind of effect those low temperatures have on the evaporation rate of a brine. Especially since temperatures on Mars can range from anywhere from minus 140 degrees Celsius to 20 degrees Celsius. If you have a eutectic brine solution on the surface, it can remain liquid for a substantial amount of time. Now, the theory was originally described by Ingersoll as the evaporation rate, or the evaporation rate being a factor of buoyancy. Okay, it's governed by how fast the molecules can move away from the surface, and that's due to a lighter water molecule going through a heavier CO2 atmosphere. So the Ingersoll equation says that the sublimation, or the evaporation rate and sublimation rate, is due to the concentration difference between the surface and the atmosphere, the density, the diffusion coefficient, and this is a Grashof term. This is Fick's law that's been modified by the Grashof term, which this is a buoyancy factor. So what we did was we put a beaker in with whatever brine that we were using at that experiment, put it on the balance and put it inside the chamber, and measured the mass loss over time. And this is what we got. This solid line is the Ingersoll theory line. The open diamonds are the sodium chloride solution evaporation rates. The filled squares are the calcium chloride. And you can see that there's a very, very strong correlation between our experimental data and the theoretical data. Originally, we had wanted to go below minus 25, but it turns out balances and electronics don't like really cold temperatures. So it kind of stuck its tongue at us and went on strike. So, and okay, we killed it. But we did get at least down to minus 25, and it did agree very, very well. So what this means is what we saw over an hour-long experiment, we lost about 2.5 grams of water at 0 degrees Celsius, but we only lost about 0.5 grams at minus 25. And if you correlate that to evaporation rates, we saw a decrease between 1.2 millimeters per hour at almost 2 degrees, and it went all the way down to 0.05 millimeters per hour at minus 25. So if you have a eutectic solution on the surface, it can last a very, very long time. It increases the stability, and the evaporation rate can slow down by 30 times at least. And it makes it stable over a good chunk of the planet. Other brine work that's been done, experiments have been done at the University of Arkansas using ferric sulfate solutions. They've gone on to hopefully work on some perchlorate. The other things that you can look at with brines is how it affects the possibility of life on Mars. There are a lot of papers out there. One, being Alfonso's papers about how salt can either help life, or sometimes if you're looking at Earth, it can also hinder life. So it's a really interesting thing to look at as far as salts are. And also, they could also affect new features on Mars today. If there's a water that's stable under Martian pressure and it leaks out, it could form these gully channels. We haven't seen any salt deposits on our gully channels, but it could just be a resolution issue. We're not sure. It's always something to think about. After we got through with the calcium chloride and sodium chloride brines, we moved on to looking at ice covered by soil. Like I said, I get this a lot when I'm talking to people who aren't, space scientists, that like, well, I don't see any water on Mars because it looks like that. And I said, well, yeah, of course, because it's under the soil. So we wanted to see, okay, what happens when you have an ice layer and you cover it with soil? What happens to the sublimation rate? How long can it last? And this is a picture of Spirit near McCool Hill. The white stuff, which I would have loved to have been salt, but it ended up being silicates, which is still really cool. God, I love that little Spirit rover. Spirit has a lot of spirit. I like it. What we wanted to know is if you have something like this, where this unconsolidated, easily churned up regolith, what happens to the ice below it? Does it sublimate faster? Does it sublimate slower? What happens? So Barney Farmer had suggested back in '76 that you could suppress the sublimation rate of an ice layer by adding a soil layer on top of it. And he even suggested that you could possibly suppress it so much that you could have melting at the ice-soil interface. This is the Farmer equation, where we see the sublimation rate is related to the diffusion coefficient of whatever soil that you have covering the ice, the molecular weight of water, saturation vapor pressure. L is the thickness of the soil on top of the ice, the gas constant, the ice temperature, and the ice density. This factor is a correction factor for the percent humidity inside the chamber. Okay. We ran these experiments to quantify how much the sublimation rate will be suppressed by a soil layer. This picture shows the same kind of beaker, but what we actually used was a graduated cylinder. So we can measure exactly how thick our ice layer was and exactly how thick our soil layer was. So we froze a pure ice layer with a thermocouple on the surface, and then we varied the amount of regolith on top, ranging from anywhere from 0.5 centimeters up to 20 centimeters. And this was JSC Mars 1 soil simulant. And what we found was we started out and we saw this nice decrease in trend, and we were like, okay, this is good. I like this. And then we started seeing an increase in sublimation rate. We just kind of went, okay, that's so not right. And we kind of scratched our heads about it, and we had one of those, oh my God, I can't believe we didn't think of this. Because as we know, JSC Mars 1 is extremely hygroscopic. It loves to absorb water. And we were running these experiments in Arkansas, in humid Arkansas. So what we were seeing was, we were seeing degassing from the soil. So what we did was we ran the same exact experiments, but with just soil, which is what this red line is. We got a very nice linear correlation between the mass loss and the regolith thickness. And I do want to point out that these values were corrected for two things. One is the temperature. If you have your sample temperatures at -10 and your atmosphere is at 0, you want to correct for that temperature difference. And also we corrected for the humidity inside the chamber. I never got very high, but what we saw was there are two different factors going on. Up to 5 centimeters, the main mass loss rate is due to diffusion. So it's due to the ice sublimating and going through the soil and being released into the atmosphere. After 5 centimeters, The main mass loss comes from the absorption of water from the JSC Mars 1 regolith. This desorption rate can be described by Langmuir's equation, which says that the desorption rate is equal to the desorption constant times the thickness of the soil layer. When we plotted the sublimation rate as a function of reciprocal thickness, we can get that correlation between that inverse relationship between soil thickness and sublimation rate. Because as you get thicker soil, you should see a decrease in sublimation rate. And we did see a nice correlation between the two. So what we found was, first of all, we did see a decrease in sublimation rate. It went from about 0.75 millimeters per hour at half a centimeter of soil, and it was suppressed down to 0.019 millimeters per hour for 20 centimeters. We were also able to calculate the desorption coefficient for the JSC Mars 1, which ended up being 1.5 times 10 to the minus 3 per hour, and that correlates very well with theory. Theory should say it should be around 10 to the minus 3. And also, the soil diffusion coefficient of the water vapor going through JSC Mars 1, we got a rate of 1.74 times 10 to the minus 4 meters squared per second. And when we calculate what theoretically it should be around 10 to the minus 4. So this agrees very, very well. Our experimental values agree very well with our theoretical calculations. Now, what does that mean? That means that if you have a meter of ice and you cover it with a meter of soil, JSC Mars 1, you can have that ice layer last 800 years at minus 38 degrees Celsius. And that is not including if you have any kind of replenishment, if you have water soaking back into the soil and adding onto that ice layer. That's just if it is released and never gets replenished. Now, they did continue this work. These experiments were repeated with fine-grained basaltic regolith, also with clays, and there have been other studies done with different types of analogs, such as glass spherules and things like that. And they all agree very, very well. Okay, wind. Now, I love these pictures. This is Gusev crater, these little wind ripples, and dune fills in Proctor crater. We know that there's wind, obviously, because we see the effects. It's also been measured. Pathfinder measured wind velocity of 0 to 10 meters per second. They've done some measurements from other satellites and from the GCM. So we know that there's wind on Mars, but we just don't know what the effect could be on an ice layer. This is the same equation that we saw before, the Fick's law that was modified by the Grashof term for buoyancy. Now, with forced convection, you can increase the sublimation rate by a factor. Well, this was the original theory, that it would be affected by the velocity of the wind to the 1/2 power. Okay, so if you have a wind, it could increase the sublimation rate. Now, we have two regimes here. We have the free convection, where the water is being removed by the buoyancy factor, and we have the forced convection regime where it's being forcefully removed by a wind layer. Our setup, we had a beaker with ice. The ice went to the top of the beaker. We placed a thermocouple on the surface. The fan was placed at optimum height to get us the maximum wind velocity. Now, on Earth, it's very easy to measure wind velocity. You just, stick a wind meter out there, and it will tell you wind velocity. On Mars, it's a little different. We don't have as many atmospheric particles to move a fan, so we had to calibrate the fans to Martian pressure. And the way we did that, we had two fans. We had a smaller fan that went from about 0 to around 3.5 to 4 meters per second, and the large fan picked up around 5 and went up to 14 meters per second. And what we did was we calculated, or we measured how much, what the rotational speed of the fan was when we applied a certain voltage, and we did it at 3 different pressures, from 1,000 millibars to 500 millibars to 50 millibars for both fans. And as you go down in pressure, the fan blades will spin faster. Okay, so as long as we know how fast the fan blades are spinning, we know how much energy is being placed onto the molecules, and so we know how fast the wind is actually going. Okay, so we extrapolated down from 50 millibars all the way down to 7 millibars. And this is where our experimental data. What we see here, this bottom line, is an area of high humidity where we allowed the water vapor just to build up in the atmosphere. And we also had experiments where we had low humidity, where we were constantly exchanging the atmosphere. We were pumping the water out and replacing it with fresh CO2. We had a pretty nice linear fit here for our low humidity environments. And we measured the evaporation rate with no wind as 0.78 millimeters per hour, give or take, plus or minus 0.11 millimeters per hour. The humidity, you can see, really didn't have an effect on it. The wind just didn't increase the sublimation rate really at all and remained about 0.3 millimeters per hour lower. The problem was when we used this equation to calculate what the sublimation rate really should be for no wind, it was 0.17 millimeters per hour, and we had just measured 0.78. So there was something happening there that was altering our results. And what we realized is that the previous equation is for if your sample temperature, your eye sample, is equal to the atmospheric temperature. So there are 2 factors we had to consider. One was evaporative cooling, and the other was thermal boundary layers. And evaporative cooling, what that is you know, if you have something that's thermodynamically unstable, it's going to want to spontaneously sublimate, but it has to get that energy from somewhere. In this case, the thermal conductivity of the atmosphere is so much lower than the thermal conductivity of the ice. Instead of pulling that heat from the atmosphere, it's actually pulling the energy from the ice sample itself and therefore cooling the sample. Okay. Now, when you calculate the cooling effect, it is dependent on the sublimation rate. This is the heat of sublimation, which is a constant. The L is the path length, so it's the diameter of our ice, and of course the heat capacity. So the actual cooling effect is directly proportional to the sublimation rate. And since the sublimation rate is dependent on temperature, at Martian temperatures, evaporative cooling doesn't really have all that much of an effect. So what we were left with was a thermal boundary layer effect. Now, we had assumed that the diffusion process and the evaporation rate and sublimation rate was dependent on the sample temperature. The colder the sample, the slower the sublimation. Instead, what we realized was that the temperature of the boundary layer is what controls the diffusion process. The warmer the boundary layer, the easier it is for those molecules to move away from the sample. So to determine this effect, we did experiments that showing the temperature change from the sample surface to the atmosphere 2 millimeters above the surface, and then 20 millimeters above the surface. And I know that looks like it's blurry. The points are so close it looks like you're seeing double, and you're not, because you know I'm holding up 2 fingers. Really, it just looks a little blurry. And what we realized was you have this ice surface here, and then this is 2 millimeters above the surface. You have a 10-degree difference. So if you use the temperature for this boundary layer, you get a sublimation rate of 0.73 millimeters per hour, which is right in the middle of what we measured at 0.68 to 0.78 millimeters per hour. So it turns out that the boundary layer is what controls the sublimation rate. Now, since we're looking at the forced convection regime, we need to know how the wind affects the boundary layer. Okay, so for laminar flow, Hisatake had described the sublimation rate as with this this term, the square root term that uses the wind velocity. But when you plot it, this is the Hisatake equation graph. This is our data. So it's quite a bit of a difference. Not only are we seeing a linear trend but, instead of a square root trend, but it's also orders of magnitude lower. So we had to look at it and say, okay, well, it's not just a laminar flow. It's not just a forced convection problem. It's a buoyancy problem plus a forced convection problem. You have to combine the two. And since you cannot use a boundary layer for buoyancy is not the same as the boundary layer for the forced convection. Forced convection has a very much smaller boundary layer. You can't interchange the two. So you have to redevelop that equation to account for both factors, if that makes sense. So what we did was we looked at the semi-empirical models and made a combined mixed convection equation. And you've seen these before, the concentration difference, the densities, the diffusion factor, the thermal conductivity. This is the buoyancy factor, and this is the factor for the wind velocity. And this straight line is that equation, the theoretical equation, or the theoretical line for that equation. When you look closer at our data, this is for high humidity, and this is for low humidity. And you can see that the new theory, the mixed convection theory, agrees very well with our data. Now, what does that mean for the stability of ice? Well, it turns out that wind isn't quite as, doesn't quite have as much of an effect as we had originally thought, especially up here in the higher temperatures, close to 0 degrees Celsius. You can see that if you go from no wind up to 12 meters per second, there really isn't that much of a increase in sublimation rate. And if you look at that more closely, you can see right here at 270 degrees, you only get an increase of about 1.5 times that, going from 0 meters per second all the way up to 14 meters per second. If you look down here at 170 K, you see orders of magnitude difference, about 2 orders of magnitude increase. Now, that's not saying that it's unstable, because at 170 K, the ice is very stable due to thermodynamic properties. But if you look at different places with different wind speeds, you will see a variation in the sublimation rate. Okay, for future work, I know that they are continuing to work with the soil work with clays at Arkansas, and they are definitely continuing the brine work with perchlorates, something I'm really interested in looking at. And I personally am working towards getting a chamber where I can look at fluid flows under marsh conditions. All these samples were static water, where it's just a container of water. It's not flowing. It's just sitting there. I want to know what happens when you flow water down a slope. Do you lose it to evaporation, to boiling, to soaking into the soil? What exactly? Where does the water go? And that's. Are there any questions?
Nice job. Are there any questions?
Mm-hmm.
At the
I talked really fast.
I'm
a southerner, but I don't know what.
At the Phoenix landing site,
Mm-hmm.
According to the reports, they have found 2 different types of ice: segregated ice, pure ice,
Mm-hmm.
thin layers, as far as I remember, and then the ice table, maybe
Mhm.
10 centimeters down there.
Mm-hmm.
So from your results, it looks like a thin layer of pure ice, somewhere 5 centimeters into the regolith, should be forming almost daily. Otherwise, you would evaporate it in a few hours, right?
You mean for like a very small
Thin layer
of pure ice? Yeah. There's obviously, I mean, like I said, our experiments were sublimating and then moving and recirculating the atmosphere, so we didn't have a sink. you know, it wasn't like it was depositing, you know, a meter down the road. So yeah, you can have something sublimating or evaporating and then redepositing a little bit later. So yeah, you can make and get rid of an ice layer pretty quickly.
The results rather show that that's what's happening on Mars. That's not ancient ice. That's the ice that's forming pretty much continuously. Right? Otherwise,
It should. Oh.
Sorry.
Yeah, it should be forming and disappearing continuously. Yeah,
Okay.
it's a very dynamic cycle.
Yeah, Julie, just to follow up on that
Mhm.
question, the sublimation rates you were getting for the regolith experiments also looked very high. I think you ended up concluding that 1 meter of ice buried a meter below the regolith would go away in about 800 years. And we know from Mars Odyssey that there is a lot of buried ice at high latitudes. Does that imply that ice is young too?
I mean, it could. I mean, like I said, it's a very dynamic process. So it could be sublimating out and then redepositing with different, you know, diurnal cycles and things like that. You know, or it could just be a temperature effect. It could be there could be a lot of things. I would love it if it was young ice, because you know, that means it's a very dynamic situation, and I'm very interested in also, you know, gullies and how they're formed. So if we have young sources of water, then that'd be
Actually, to follow up on this
fantastic.
question, how is this diurnal cycling going to affect or suppress the sublimation rate and also the boundary layer thickness?
That's a really good question. I didn't look at that as much. I know that if you look up the paper by Brine and that group, you know, from University of Arkansas, they did look at the diurnal cycle and how it affects sublimation rates with basaltic, fine-grained basaltic sand. So I wish I could speak more intelligently about that, but
And that might serve to shield or enhance the sort of thermal equilibrium with the different daily cycles.
yeah, I mean, if you know, it depends on if you have a soil that will conduct heat and keep keep heat. You know, that could affect the underlying ice table, and yeah, there's a lot of factors that go on with the diurnal cycle. It's like I said, with my work, we didn't look at that as much. We wanted to use a solar illuminator to mimic the cycles. Unfortunately, we didn't get to that before I left. You never know. Maybe I'll go back.
At the end, you mentioned perchlorate. What are the suspected concentration of perchlorate in the Martian soil?
To be honest, I am not sure about the concentration. Less than 1%? Okay, a bit less than 1%. So now I haven't looked at, you know, how that affects, you know, sublimation rates or anything like that. It's something that's really interesting, especially since it's such a hygroscopic, you know, molecule that, you know, perchlorates love to soak up water. So it's a really interesting question, and whether or not we see it elsewhere, it would be really interesting to find out if that's what the anomalies for a Viking. I would love to see that be perchlorates, but we'll see.
Does this work allow you to model the behavior of Mars polar caps and how they recede and reaccumulate on a seasonal basis?
Well, you can use this looking at the sublimation rate and how quickly it does take to disappear. I did not do any computer modeling using that, but I do know people who have, and this would either validate, you know, you can use that to validate your computer model theory, or, you know, alter it in some way, or yeah, you can absolutely use it.
Actually, it was nice to see how well you could fit or describe your data with theory, and that the correlation was really appealing.
Yeah, and
so
yeah,
that's what
really
I was
exciting.
I was going to ask you if you have plans to follow up with additional modeling work yourself to
Well,
extrapolate these to other conditions.
Personally, I'm not sure if I will do it. I like getting my hands in the lab. But you know, even if you get something in the lab, you have to compare it to your model. I mean, there's no other way around it. And it's a very useful, really useful tool. Whether or not that's a hard question to answer. I'm
Something
not
else
sure.
to do.
Yeah, I know, it's something else on my